Morning, friends. I have devised a game with dice. I call it the game of dice. Suppose one is throwing a dice and summing the digits turning up. What is the expected number of throws to reach 10 or above? So, in one throw, you cannot reach 10 because 6 is maximum. So you need at least two throws, and maximum is 10. If it turns up 1 in every throw, it will take 10 throws to reach 10 or above. So what is the expected number? Then what is the probability of reaching exactly 10? What is the distribution of the overshoot? What is the distribution of the last digit to reach 10 or above? So I tried to address these problems through simulations only. So let me refresh the screen. Okay, now I am tossing the coin. 1 comes up, 5, so the total is 6. Now it is above 10, which is 12. So 1, 5, 6, that's the sequence. Then I go on tossing and recording the numbers. Nine, now it is 10. So this is exact 10. So out of 4 throws, one has made exact 10. So the probability is 23%, and the sequence is 3, 3, 3, 1. So here I am doing the histogram or the counts of the stop time. Twice I made 3 throws to reach 10 or above, and then it took 5 throws, only 1. So this is the distribution of stop time. This is the distribution of last number. 3 has come once, 6 has come twice, 5 has come once. So 2 plus 1, 3 plus 1, 4. 3 plus 1, 4. So total number of throws is 4. And the overshoot, it was exactly 10 once. So the overshoot is 0. So that happened once. And overshoot is 1. That happened once. And overshoot is 2. That happened twice. So this is just the simulation. I'll continue the simulation till the face of Theron comes back. Face of Theron comes back when it is exact 10 in an increasing sequence. So it is 2, 3, 5 increasing sequence, and the sum is exactly 10. So let me do it once again. I have refreshed it. Sorry. Four throws, 5 throws, and once it was exactly 10, but not in increasing sequence. Now 4 and 6 increasing sequence. So I have made 7 throws. Once it has reached exactly 10, so the relative frequency or the approximate probability is 14%. Maximum number of turns I took is 4, so that is recorded here. And these are the distribution of stop time when it is stopping in 3 throws or 4 throws. And expected number of stop time is 3.14, between 3 and 4. And this is the distribution of last number. This is the distribution of overshoot. I was working on a write-up. I'll show you the write-up. Getting a total of 10 in dice throw. So I calculated this chart. Number of ways to reach a total of S in n throws. So here I have S and here I have n number of throws, and these are the different counts. There are 252 ways to reach 11 in 6 throws. So these are the counts, and I got the probability of reaching exact 10 is 0.2892, near 0.3. So around 30% cases you will reach exactly 10 when you are stopping, when it is exactly 10 or above 10. So 0.2892 is the probability of reaching 10. I calculated it theoretically, and expected stop time is 3.32. So it takes more or less 3 or 4 times to reach 10 or above in a dice throw on an average. Then I calculated theoretically the distribution of overshoot. These are the probabilities, and the overshoot can be 0, 1, 2, up to 5. If the total is 9 and you get a 6, you reach 15. There is no other way to reach 15 when you are stopping, when it is exactly 10 or when it is 10 or above. So this is the distribution of overshoot, and this is the distribution of last phase. Last phase can be 1, 2, 3, up to 6. If you get 9 in total, the last phase 1 comes up, then it is exactly 10 and you stop. Now there is an interesting similarity between the distribution of overshoot and the distribution of last phase. Say ONR denote the number of ways overshoots R can happen when stop time is N, and LNR denote the number of ways last phase R can happen when stop time is N. Then ONR is L of N6 minus R. So I'm trying to prove it. Hope I'll finish the write up properly. So now there is some generalization. I can go for a generalization. So here it is. Here you fix N up to 10. Whatever. Okay, it has refreshed. So here I replay, instead of 6 for dice, I took the number 9. So you get all the faces up to 1, from starting from 1 to 9, and you stop when it is exactly 9 or above it. So let me do some simulations for 9. 14 is above 9. So the sequence is 5 and 9. 1 plus 8, 9. So it has stopped here since it has reached 9. And for this general setup, one can talk about the distribution of stop time, the distribution of overshoot, the distribution of last number. So I'm working on it. I'll stop here. Thank you.